Yeah,
Okay,
so
I'm
today I
going in.
wanted to talk about the
Okay.
problem that is the dungeon problem statement. Today we are going to look at its statement and how it can be solved in two alternative ways, and the pseudocode of one of them, of the most efficient. So what's the problem? Is that we are trapped. Suppose we are trapped in a 2D dungeon, and we need to find a quickest way out if it exists. This dungeon is composed of these unit cubes in a grid. Uh, so yeah, and each of the unit, which of this cube, can either be filled with rocks or not. So we cannot go through the block with rocks that is blocked for us, and also we can. It takes 1 minute to go either north, west, north, south, east, or west. And and also we cannot move diagonally. And we want to find the shortest path if it exists. If the escape, we want to determine if the escape is possible, and how long will it take us to get out of this maze. And also we cannot go out of its bounds, so it is surrounded by solid rock on all sides, and we can go through this. All right, let's look at the problem itself of what is it. We can represent it as a grid of size r by c, and we start from the node s character with the s character, and want to finish in node e, that is the exit cell. So the cell full of rock that we can go through is indicated by this hashtag or pound character, and empty cells represented by dots. And we want to.
Where's the entrance? Where's the entrance?
The entrance is at S character.
Oh, S. Okay, thank you.
Yeah. So. Yeah, this cell is. One moment. One more thing to do. Yeah, so we're starting at node S, and we have to go to node E. We have to exit at cell E. So in this particular situation, it is possible to escape using this path. Also, we want to find the shortest path, not just any path, to escape the dungeon. So our approach is going to be use a breadth first search from the start node until we reach the end node, and want to count the number of cells we traverse here during this process. However, if it might not be possible to exit the dungeon, we want to return that it is not possible. We cannot reach the exit, so we have to be mindful of that. We have to consider the situation if that is impossible. So, for example, if the end node, the exit node, the cell is blocked or whatever, these situations are also possible. So let's look at the demonstration of how this works. So this way. So we need to start by visiting our starting node and adding it to the queue. So let's assume that we already found its coordinate. It is given by the statement whatever, and we want to add it to the queue. So we're adding it. We add this cell to the queue. And we're starting our traversal algorithm. We visit all adjacent, unvisited neighbors, and we add them to the queue as well. And we're continuing this process. We continue this process just like any breadth first search program. Avoiding adding these rock cells, so we do not want to add rock cells to the queue, and do not want to consider them while while finding the shortest path, because that is ridiculous to add them. All right, so we want to, and we're predict in this way which cells will be visited next. In this way, this is how the traversal works, and we found the end node. As we reached it, we now know the shortest path. We reached the end. So if we want to regenerate, reconstruct the path, we can make a Prev matrix, a 2D Prev matrix, but in this particular situation we do not want to. We are just looking for the amount of steps to get out of these maze. All right. And if we want to retrace these steps, we would have a Prev matrix. All right. So this is how this works, and also an important thing. So notice that here, as soon as BFS hit the exit point, that means that we have found the shortest possible path. But however, with depth first search, that does not work. This does not work in this way because there might be a shortest path that we did not visited with this depth first search traversal algorithm. That might be, and we need to look through each cell. However, in this particular situation with this BFS, using BFS, we do not want to visit each cell. We just want to hit the end point. So here, this bottom right cell is still unvisited, and that might be so in this case, in this way, using breadth first search, we might not visit all the cells, and that is possible, that is normal. All right, so next, let's talk about alternative representation of this algorithm. We can store these this next XY position, in this pairs in the queue, in the way of this XY pair. So this works well, of course, but this requires an array or a wrapper such as pair data type in C++. It might require pair to store the coordinate values x and y, and also here in practice this would require a lot of packing and unpacking of values, so the program would be overwhelmed with these dot second, dot first in C++, as we are unpacking the pair, or if that is higher dimensional, higher dimensional maze. If we want to 3D, if we want to find the shortest path in 3D maze, whatever. So it would take a lot of efforts to set up this data, to set up this algorithm, and for example with 3D, that would require pair of pairs in C++, or that would require tuple, or how this word, vector of vectors, whatever. So this is why we would do another algorithm. Let's look at it in one moment. So an alternative approach here is to use one queue for each dimension. So what does that mean? That means, so in 3D grid, we would have one queue to track the x, y, and z dimensions. So let's look at the example. We want to enqueue the current position x, y, z, and would enqueue this to for each node, for each dimension, to its own queue. So x queue, y queue, and z queue. Yeah, so we could simply place each coordinate with their respective queue in this way. Yeah, and to enqueue another position, we simply keep filling the queue in this way, the queues in this way, and so on. So this contrast here, that the contrasts the approach of simply having one queue with each component with a pair of pairs, whatever, packed inside the object, is that we have to unpack these, and we have to be mindful about how to enqueue or dequeue elements, how to enqueue and dequeue elements in this particular way, in this representation, this alternative representation. How to do this? The answer is, we want to dequeue or enqueue from each of the queue at the same time. So for example, we want to dequeue, we are pulling elements from each queue, and we need to remove from each of the queues. In this way, so we're removing them, and for example, for the second, for x2, y2, z2. So this representation is preferred while working with multi-dimensional coordinates, and this is why we want to write our algorithm using this using this representation. It is a lot more obvious to, readable, a lot more readable thing, because these pair of pairs with infinitive unpacking is pretty unobvious to read. Is not very user-friendly thing. Reader-friendly thing. So let's look at the pseudocode for this dungeon problem. With all of these knowledge, assume that we have already read the matrix, the input matrix, and we have did all this pre-processing to find the starting node, whether it is given or we have found it ourselves. So the first two variables we want to declare are number of rows and number of columns. For example, we want to input these. And M is input character matrix of size R by C. R by C. Next, we have the coordinate. The next thing is two variables, CR and CS, that represents the starting node. So we need these to start our breadth first search. And next are RQ and CQ. These are two data structures. These are two queues, empty row queue and column queue. And we're going to enqueue and dequeue elements during the breadth first search. And the next thing is, the next set of variables is these three variables to track the number of steps taken to reach the exit. So move count would actually track the number of steps taken. That would be the answer. Nodes left in layers. This tracks how many nodes we need to dequeue before we are taking a step. And the third thing is nodes in next layer. This tracks how many nodes we added in this breadth first search expansion. So we can update these nodes left in layer accordingly in the next iteration. This would make sense soon. So reached end will track whether or not we reached the end, and that is marked with the E character if we got the answer. Next is visited matrix, R by C. So we're going to use this thing as with the same size as the input grid, of course, to keep track of whether or not a cell has been visited. Since of course, we do not want to visit a cell twice, because we want to find the shortest path, and we do not want to create cycles. Yeah, and lastly, we define the north, south, east, and west directions vector. This thing we talked about last time. And yeah, let's look at the solve function, the solve method within our solution. So this is the breadth first search code, by the way. First we enqueue where we add the starting cells, row and column values to the row and column queue. Yeah, and then we are making this visited array at the starting position equal to true. By the way, we can also make it equal to 1, and because integers matrix are a bit more are a bit faster than Boolean vectors, Boolean matrix, whatever. We don't want to go to the starting node again, and then we're starting our breadth first search traversal while one of the queues, by the way, yeah, our row queue or column queue, whatever, are empty because we are dequeuing and enqueuing at the same time. All right, so while its size is greater than 0, while it is not empty, by the way, we can use .empty method in C++, whatever, and yeah, we're making these values of queues to be in synchronization. Yeah. So since we know the queues aren't empty, as we have just visited, we are dequeuing the current position from the queue, and yeah, and saving their values. That is R and C. This is we're processing now. And next, so if the node we're now at is equal, its value is equal to E, that means we have reached the exit. We're making this reached end variable to be equal to true. That means, yeah, we have reached the end, and we're breaking. And next, we're starting explore neighbors method. So if it is not the exit node, then that means we're starting to traverse all its neighbors. We start to traverse all its neighbors. Yeah, so let's have a look on this function. So inside the explore neighbors function, we have a method that where I'll be using this direction vector technique we've looked earlier. So yeah, a cycle of 4 directions we want to check, and yeah, we're traversing through its neighbors, compute the new coordinate that we're now at. If it is out of bounds, we're skipping it, and also we have to make sure it is not visited, or it is not closed, it's not blocked off. So if it's traversable, if it's not traversable, we're skipping it, and next we're dequeuing, and we're enqueuing the node we're now visiting, and making it visited, and adding adding by 1 we're adding one. We're adding one to the nodes in the next layer variable. We're incrementing. Yeah, we're incrementing the number of nodes in the next layer. We'll need this shortly. Yeah. Next, this block of code is used to track the number of steps we took getting the dungeon exit. So each time we finish a layer of nodes, we increment the number of steps taken, and we're at first we're incrementing the number of nodes, the number of steps we have already made, and also we're making the nodes left in the layer variable value to be equal to nodes in the next layer, and we're making the value of we make the value of nodes in the next layer to be equal to 0. And before that we subtract by 1. Yeah, we're decreasing this value by 1 nodes in the next layer. Yeah, and this way we're tracking the amount of steps we have already made. Yeah, and this way it works. And next, as we left the while cycle, if we are able to reach the exit, we return the move count. Yeah, the amounts of steps we've made. Otherwise, we return -1. That means that the node is not visited. Yeah, let's make a short summary of what we've learned on these grid. So we can represent a grid as an adjacency list or an adjacency matrix from just an empty grid. We can use direction vectors to visit neighboring cells and even diagonally. And it is a lot more convenient to use this cycle of 4 or of 8 than to copy paste 4 or even 8 lines of code to check each thing, to check each cell. Next, we've explored how to represent multi-dimensional coordinates using multiple queues without using pairs of pairs in C++, whatever. And finally, we know how to use breadth first search on a grid to find the shortest path between two cells. So that is the breadth first search on an implicit graph. That is one of the last topics that we've learned at Sirius. After that, we've only looked through some advanced things like DSU and this thing, how it is in English, минимальное остовное дерево. How it is? Minimum spanning tree. Minimum spanning tree, of course.
Spanning tree. Oh, okay. Minimal spanning tree. Yeah, I know.
In Russian, that is called минимальное остовное дерево.
Okay.
So now I'll wrap up here. This was a talk on thank you, a talk on using breadth first search on an implicit graphs. Thank you, Robert.
So you're ready for your next dungeon. So if you're stuck in a dungeon, if you are stuck in a dungeon, you know what to do. Dungeons. Here, let me calculate this minimal spanning tree. Okay, so no, interesting.